Okay, our next speaker is Dr. Ron Yurko. He's an assistant teaching professor at the Department of Statistics and Data Science at Carnegie Mellon University. His research focuses on developing methods at the interface of inference and machine learning oriented towards problems in statistical genetics and sports analytics. He previously received his doctoral degree at Carnegie Mellon and has industry experience in both finance and professional sports. Take it away.
All right, thank you, Scott, for that introduction. I'll do my best to follow Ryan's talk. I will say that I've been fortunate enough, this is my third talk here at NESSIS, and there's kind of a saga of progression, per se, in the work that I have leading up to today's talk. So, sort of episode one, we're beginning with the traditional view of sports data analytics, of thinking of game states at a very discrete level. I have a starting state, say the beginning play value, and I have an ending state, and I think about like the changes in those values for attribution of players. I have the expected points added. So this NFL Scraper Menace in episode one, NESSIS 2017, as Ryan just did the takedown of modeling expected points. So thinking of expected points as I have this design matrix X corresponding to my down, my yards to go, whatever information I have. Maybe I'm starting to actually account for team strength appropriately. But ultimately, those spitting out predicted probabilities of the next scoring event. And I could accumulate those probabilities with some associated point value, and I can get my expected value for a particular state. But that's an oversimplification of sports. All right, sports are not just discrete states. Maybe baseball is, but football is a much more complicated game. There's a lot of action going on in between the plays, and what I really want is some notion of within play value. So episode 2, 2019, was Attack of the Tracking Data, where we had the big data bowl enter in, and we have, so just for context, NFL is chips in the shoulder pads and the ball. We get information every 10th of a second, where players are on the field, their velocity vectors, orientation that they're facing. This was an example play from that talk where I focused on NESSIS 2019 of modeling player movement, predicting where a ball carrier is going to end up on the field. So I have just a single example play here corresponding to a 47-yard touchdown run. So the team on offense in blue, team on defense in orange, and the ball carrier, Cordell Patterson, who was a wide receiver at the time, going to get jet sweep handoff and ultimately going to score a touchdown. But what I care about is this notion of how does that play value change within the play itself, this notion of expected points, win probability, whatever utility function I have of interest. And so what we want is some updated prediction of what the ending yard line is, because ultimately that's all these utilities in football are inherently functions of. I have some predicted ending yard line, and I feed that through whatever this utility value function corresponds to. In this case, my expected points multinomial logistic regression model, update my design matrix with the new ending yard line, spit out the new probabilities, accumulate, get a expected points value. What I care about is a full expected value of this utility function. So what we need is a full distribution estimate to integrate over. So G here is my expected points, win probability, whatever I want it to be. I'm just going to focus on expected points in this talk. And what I need is a conditional density estimate, so this distribution estimate of what the ending yard line should be. And so what I'm going to do for this today is use what's called random forest for conditional density estimation. So this approach, innovation of high dimensional conditional density estimates from collaborators in the CMU statistics department, focusing primarily on modeling tropical storm, cyclones, and other, and also astrostatistics data, and might as well port it over into the football tracking data space. And so the idea here is, again, V corresponding to some value I have, and I want to get this expected value given the information I have within a play. And so I need a full distribution estimate of what the play looks like. So this is at a particular snapshot in time for this example play I just showed, where the red lines on the field are corresponding to the density estimates. The brighter, the darker the red intensity, that corresponds to, on the bottom plot, the higher relative likelihood that the player is going to get tackled at that spot on the field by the end of the play. And then you have this little mass here over at the left-hand side corresponding to like a non-zero probability of the ball carrier reaching the end zone for a touchdown. All right, so a full distribution estimate, each yard line has a value associated with it. And then I can integrate over these density estimates to get then my expected value, my expected within play value at that particular moment of time. So the toll of the day, all right, is RFCDE. So this is episode 3, this talk is really Revenge of the RFCD. I'm gonna use this a lot. And so what this actually is doing is a weighted kernel density estimate, where you're learning weights based on your high dimensional features. And so this corresponding weight up here is just saying, okay, if a particular value of interest X falls in these same terminal leaves for a random forest that I have, all right, a collection of T trees. So for each tree, you observe, does my value of interest, given this high dimensional vector, does it place within each of the different observations and their observed vectors of features that I have? Average over the T trees to get sort of the average weight, and then you plug those weights in to whatever your kernel density estimate is for your value of interest. So I might be looking at a density estimate for the yards gained by the ball carrier, and all I'm doing to account for all this potential high dimensional tracking data information is some smartly informed weights that were created via a random forest model. And you could do very different approaches for this. I'm using random forest because I'm being lazy today in how I'm thinking about things. It's nice off the shelf. But the other key feature of just this implementation is that the tree splits are actually chosen based on a loss function particular to conditional density estimation. All right, so that's great. I'm not going to speak any more about the details of that. I'll leave it to the professionals in this paper at the bottom. But I'm going to leverage this for both 1D and 2D conditional density estimation, rather than explicitly computing what conditional density estimates are for, say, a very high dimensional suite of features. Or we're using informed weights from a model. So in continuous time, potentially, we could create these full conditional density estimates throughout a play. So you're seeing here how the conditional density estimates change throughout this run, noting then some increasing non-zero probability at the end corresponding to the ball carrier reaching the touchdown. And with that, I can get full continuous within time, within play valuations. All right, so the top chart corresponding here to an expected points throughout a play, and the bottom corresponding to a win probability. All right, so some utility, and I'm getting the within play value. Now that's great. What I want to know is, how do I actually assess player performance with this information? These models are based on player tracking data, based on the locations and the velocity vectors of the players. So this is not an average representation of what we expect to see within a play. This is conditional on all the players, the schemes, and how everybody is moving throughout the play. So what I want to know is, how can I actually look at this curve and get a sense of what value a single player is adding, maybe at a single moment or across the full play, relative to maybe some notion of an average player. So I'm going to think of what I'm calling a trivial example for this talk, where I'm going to focus on just the yards after catch. So this work began with the Big Data Bowl 2021, which was evaluating pass defense. Fortunately, it had all passing plays from the 2018 season, but the NFL can't be generous enough. They have to remove linemen from the data as well. But what we're focusing on, so there's two components to passing plays. Once the ball is actually thrown, you have the air yards, the ball traveled in the air, and then you have the yak component if the ball is successfully caught. All right, so the yak component, the yards after catch, top panel corresponding here to just a sense of the distribution of the yards corresponding in gray to through the air versus yards after catch in blue. And then, even though, as Ryan noted, it's incorrect, at the bottom here is the NFL Fast Star expected points added, just from the air in this gray versus after the catch in blue. So the whole point of this slide is to make the point that yards after catch is important. So how can I think about ways of evaluating defenders and their ability to suppress yards after the catch, but in the value that I'm interested in? All right, I care about things on a point scale or a win scale, right? Because those are transferable. I can actually communicate those quantities in some way. So I want to get a sense of how can I evaluate players with this tracking data formation construction that I have in a point scale basis. So again, I'm going to focus on yak, and now I'm going to simplify things further by just focusing on a particular moment in time, the moment of catch. And so as before, this is just a reminder, to get the expected value within a play at the moment of catch, I need to integrate over a distribution for what I believe the yards after catch distribution looks like. So I'm going to begin with a conditional density estimate for the yak, given information I have at the moment of catch, X catch here. All right, so modeling a full distribution estimate with this RFCDE model of where I believe a receiver will end up on the field after they catch the ball. And so part of this process involves extensive feature engineering in how I'm performing this operation. All right, so I'm constructing information about the location, velocity vectors of the receiver, information about their teammates, everything ordered in with respect to the distance to the receiver. So I have defender 1 information corresponding to the closest defender at the moment of catch. Offensive 1 information, the closest teammate to the receiver at the moment of catch. I have information about the quarterback at the moment of release, so knowing about like the length of the pass directly, the speed at which the quarterback is moving. And ultimately what we view, so again, just this visual is just showing you just a sense too of the feature construct is about relative to the ball carrier. So noting the difference in the angles of the orientation the players are moving, the actual observed distance that we have between the players. And ultimately what I observed based on leave one, week out, cross-validation performance, the most appropriate model that I had in out-of-sample performance for modeling this yak distribution was just a function of the receiver level, location, velocity, vector information, the QB information at the moment of release, and information about the closest defender, their location and velocity vector information in relation to the receiver that they were nearest to. All right, so this simplifies my problem further in the sense that if I just want to evaluate the defense at this moment of catch right now, I'm just only going to be thinking about that nearest defender. So I'm going to pick an example play here. This goes from right to left. So offense in blue and defense in green. And so what I'm focusing on here is cornerback in red, Jerry Alexander. And I think this was a play, it was on a 3rd down, a 3rd and 6 or a 3rd and 7, where Jerry Alexander, at the moment of catch, so the receiver here in blue, he's right on top of him, and that actually makes the tackle, all right, shuts him down before the first down line. All right, he stops him. All right, he suppresses the receiver from advancing any further to obtain a first down. So what I want to know is the value of that positioning of this corner at this particular moment in time. And so at the bottom here, I have what my distribution estimate looks like for the yak for this coverage, given this information about their velocity vector location information. And you can see the mass of this is before the first down marker. And so if I integrate over this distribution estimate with each corresponding value I have associated with each yard line, I have a negative EPV. All right, a negative expected play value within this play at this particular moment of time. From a defensive point of view, that's great. All right, it's a negative value. That's what we want to see. But what if I move that player around in some way? What if that player was in a different location with a different velocity vector? So I can imagine I could just pick like one particular spot on the field, and then I could see probably a whole new distribution estimate in some way. But point estimates are dumb, all right? What I really have is some relative likelihood over some space here defining where I would expect to see just a distribution of defenders being drawn from. And I need to quantify that uncertainty then about where I might visualize and see other defenders moving it with particular velocity vectors. So if I take away the corner here on this play and I just have the receiver at that moment of catch, again, I want to think about where these ghost players could potentially be, some relative likelihood of observing them in different locations. And so again, I said this is revenge of the RF CDE, so all I'm going to do is a 2D conditional density estimate of where defender locations could be, given information I have about the receiver at that moment of catch. All right, so the intensity here is corresponding to a 2D conditional density estimate of the nearest defender location. All right, so I'm conditioning on them being the closest defender, hence this defined radius of distance less than the second closest defender. All right, so I'm already conditioning on that role for this particular player. And then I have the intensity of this, so yellow corresponding to a higher density estimate of being at this particular location on the field, and blue being low. And what you can kind of see is asymmetry here. And that sort of also motivates the purpose for a flexible approach. I'm not entirely certain what distributions I would expect to see for player locations in different ways. Right? We're dealing with complex spatial data. And if I had more information maybe about scheme, which I don't here, maybe I could make some simplifying assumptions. But I don't know what the coverage type is. I don't know anything about that. I'm just dealing with raw tracking data. And so what I effectively do, though, is looked at, out of sample, how to appropriately model this 2D density estimate and see that varying different degrees of features in terms of just conditioning on information about the receiver versus conditioning on information about the teammates, all I need to have a good distribution estimate at the moment of catch here is just information about that receiver. And so I'm modeling then a defender's location with respect to information about the receiver at that moment of catch. So again, I want to get a framework for evaluating then a player on this expected point value scale. And so I have my EPV for a catch, but now what I need to do, make myself look smart, I'll do multiple integrals here. All right, I'm going to integrate over a distribution estimate for the player location. So this L here is corresponding to a 2D XY grid of the player locations. I have my 2D conditional density estimate of player locations given information I have about the receiver at the moment of catch. For each of those locations, I update my design matrix that goes into my YAC CDE estimate, updating where the nearest defender is, generate a distribution estimate for that particular ghost location, integrate over with respect to the point values for those plays to get an EPV value of every location, and then integrate over my 2D locations of the ghosts to get a total expected value of ghosts. But this is ignoring something. This is completely ignoring the velocity vectors of the players as well. All right, I'm only doing the 2D locations. And how I'm going to handle the high dimensional nature of player velocity vectors, the speed, the angles, their orientation, is through sampling. All right, so I'm not going to directly model that information. I'm going to really abuse notation here. And what I'm going to imagine is I have some table corresponding to all the velocity vectors I observed throughout a season for the nearest defender. And so what I'm going to do is for every single 2D location that I'm considering, I'll draw B draws from that table of velocity vectors, preserving the correlation between the speed and angles that they move in. And I'll just integrate over that as well, compute the average value associated with the locations based on averaging over B draws of velocity vectors, ultimately then integrate back over my 2D grid to get then this expected value of player ghosts based on a density estimate for YAC, a 2D density estimate for player locations. All right, so full distribution estimates for where players are at on the field, but being lazy about the angles and speed at which they're moving. So this is a visualization of that particular play corresponding to the EPV values at different locations on the field. And so what you can see here, going from a blue EPV, blue being like the negative value, being low, good for defense, and then moving further away from that to being good for the offense. You can imagine this is as if I move the player, the defender, around this grid on the field and how it changes then in terms of this expected value in relation to what we might believe then the yak would be for the receiver at the moment of catch. So the player that we actually observed was right on top of that defender. They're in the blue zone, they're in the cold zone, they're in the great spot for the defense. And so what I could do now is I could compute this expected value at the moment of catch, given the player's location velocity vector information as a negative 0.16 value. And then I could look at what's the expected value across this distribution of ghost estimates. And that corresponds actually to something that's positive on average. All right, this whole distribution integrating over the ghosts is something about 0.77. So I could take the difference then and imagine what I'm computing now is what I'm abstractly thinking is the value added corresponding to the player being at that location with that particular velocity vector at this particular moment of time. And in this case, it's nearly worth a point in value. The player being at this location in which they are ultimately suppressing the receiver from advancing on the third down to get a first down. All right, so I can do this accumulation across an entire season's worth of data. And so what I'm giving you here is the top 10 corners in terms of their total change in this EPV value. So not just corners here, top 10 pass defenders. And so the point of this table is just to get a sense of on what scale do I think I'm actually having a total point value and an expected suppression of yak. And so what I'm saying here is over the course of this season, based on this approach, I'm having like a touchdown's worth of suppression based on the player being at a particular location on the field with its particular velocity vectors across all their plays that they're involved in, where they did technically are observed as the closest defender on a reception. All right, and so just to give a sense of how it varies in terms of the naive scale of thinking about yak, or yards after catch, it's shuffled around here because that's not taking into account the context. And we would think that defenders and how they're used and their positioning will be varying to the degree of that context as well. They might be allowing more yards after catch if there's flexibility for the team to do so. All right, so this emphasizes why you also want to put this on this value scale. But to put it on a value scale, you need distribution estimates to integrate over. These value functions are not simple. They're coming from whatever types of modeling approaches, and then you'll throw in a catalytic prior to make this even more complicated. All right, so just to recap what I've just done here so far, about introducing a framework for evaluating players based on this integration over both this ending position for the value of a play, as well as distribution estimates for what we believe we might observe players to be at, given potential things we condition on. All right, so I cannot attribute, though, my PV entirely to the players in these play, all right, without recognizing whatever scheme call might be deciding why that player is in that particular spot at that particular moment of time. That might play a larger role here. I don't know. I don't have that data. And I'm only considering the closest defender, all right? I'm imagining conditioning on everybody else on the field at where they're at. Let me move this particular player around. And what impact would that have on the play in this hypothetical abstract sense? I'm not changing the entire defense. And ultimately, I would imagine players are correlated with each other in different ways. So this might be an unrealistic approach, all right? So that's a limitation of what I'm doing here. And I'm also, as I said, this was trivial, I'm only focusing on yak, all right? By definition, a reception has been made, which is bad for the defense. So those 7 points, 6 points, whatever that I've said they've done that's worth in terms of where they're at the moment of catch could be just washed out by whatever value they gave up by the catch. I don't know the answer to that because to do this prior to the catch, I need more modeling. I need models for targets, models for reception, and I need to propagate then all these distribution estimates throughout those different models to make this expected value function even more complicated to compute. Now, the other thing I've completely ignored that I began this talk with is continuous time. All right, so this is a single example play. Again, the same cornerback covering, in this case, it's Adam Thielen, a throw from Captain Kirk. And he converges on the receiver at the moment of catch, But then you see this blue dot of a player ultimately doing a block. And I'll admit, I haven't watched this play. Or I'm a professor. I don't have the time to watch football. That's not true. But we see the defender misses the tackle in some way, and the receiver goes on to advance, and they nearly get a first down. They get like 8 yards on this play. So what I could do is I could compute the full continuous time EPV curve from the moment of catch. All right, so I'm being lazy here. Again, I'm not thinking about all the other models I needed to do prior to the catch. But starting at the moment of catch, what is the change in expected value given distribution estimates for the yak for the receiver based on the observed information? And I can see this big increase and then a leveling off in a certain way. Now what I could do is imagine changing the defender, that nearest defender, and computing the EPV for the ghost defenders. So now this red line corresponds to my EPV for when the closest defender at every moment of time has been replaced with this distribution, the average ghost value in some way. And so I now can compare these curves, the values across within a play. And so I could say, okay, the red line here, initially, I'm imagining that there's very positive, the defender and where they were at, just based on this defender level information, look great. Their blue line, their observed blue line is below the red line. But there's a point, likely due to that blocking of the player, that this was a really big swing in value then, corresponding to that action, that moment of time. And maybe I could put that point value now on that action, that block, that missed tackle, whatever it may be, to attribute what was a core moment in the play. And then for the rest of the play, you could see that approximately the movement of the players, the closest defenders, matches sort of the expectation in this valuation. But this kind of goes to show the difficulty of this problem and extending it to continuous time, why I just focus on a single snapshot. And the way I've constructed my feature representation here, I've done it based on player roles. I'm looking at the nearest defender. That nearest defender changes over the course of a play. So portion of this time, it's going to be that corner. A separate portion of the time, it's going to be different players. All right, and so then I have to think about how will I carefully tabulate all those changes to construct a proper continuous time value added or subtracted based on players given how they're moving, their locations, and their particular velocity vectors. So that's episode 4 for next time. But I just want to thank, this is joint work with Kostas Pelekrinis over at Pitt. Thank Dr. Ventura and Dr. Nick Del Masso for some feedback on various things, and I'll do my last pitch as well, following up on Kwong earlier, to make sure to check out upcoming Carnegie Mellon Sports Analytics Conference in November. And with that, thank you, and any questions?
Thank you, Ron. Time for 1 or 2 questions. You ready?
Hey, thanks. Aaron Barzilai from HerdUpStat. So, Ron, this is super cool. I was thinking about it, whether it be episode 4 or maybe even episode 5 versus, I think really my question, or how straightforward is that, I was struck in your example, right? We were pretty focused on that play close to the, I guess, first down marker, right? And you could see in the bottom left that there was pretty good deep coverage. So I was wondering, could this be extended easily, or would it be really hard to sort of, the value of coverage sort of persuading the quarterback to check down versus try deeper passes, essentially giving credit for the folks that aren't getting many passes thrown to their receivers because they're so great at defending it that the quarterback doesn't even want to try.
Yeah, no, that's a great point. I think of just getting a sense of what I would imagine is sort of a condition on knowing what a particular coverage scheme looks like. I can probably have a much cleaner estimate of player location, all right? And I could come up with, okay, condition on a particular scheme, we'll have some heat, mass, density of players being in a particular spot, and maybe I could compare that back, knowing certain coverage schemes might have a much wider looking distribution. Other coverage schemes might tend to have a much more local distribution potential. So I mean, I don't know. I mean, that would be wonderful to try to do with that additional data as well. But I mean, your point is valid. I think about it, comparing based on that value. Thank you.
All right. One last question.
Nick Oza from Big League Advantage. Thanks for the presentation. Great presentation. So for the sampling of the velo vector, that I guess you're doing with the velo vector kind of autocorrelated with the other velo features. But wouldn't the velo vector also be dependent on the location or vice versa? Are you building in any dependence there?
Yeah, no, it's a great point. Right now, I'm just completely ignoring that. And you can imagine that it really should, I would think they're correlated together. So maybe first condition on the location, or even just like the distance of that location to the receiver, and maybe just do a more informed sampling in some way. Like weight the velo vectors based on what those distances were. That might be a great thing to do in the paper, actually. Thanks.
All right. One or two quick announcements before we close. If you have a poster, please make sure it's up as soon as possible. And then we're going to have an hour for lunch. So with that, we'll close this session. Let's thank all of our speakers.